Let's take a look at Hall's theorem. The theorem gives us a condition on when an SDR exists for a sequence of sets. The theorem does not give us a method on how to find it, but it gives us a way to check whether there is or there is not an SDR for a sequence of sets. The way the theorem is written, stated, it seems complicated, but it's actually pretty straightforward. So let me read it first and then I'll illustrate with an example. The sequence of finite sets S1 through Sn has a system of distinct representatives, an SDR, if and only if, whenever I here is a subset of the set of numbers 1 through n. Whenever I is a subset of that, then the corresponding union, and I'll explain what the corresponding union here is. If the corresponding union contains at least as many elements as the set I does. Okay, let's say for example you have 10 sets S1, S2 through S10. The set I that the theorem is talking about here is the subset of the set of numbers from 1 through 10. I is a subset of 1, 2, 3, all the way to 10. Notice that I is not a subset of S or any of those original sets. Set I would be used to indicate which of the original sets you're going to pick. For example, I can be 1, 2, and 4. Or the set I could also be, I don't know, 2, 5, 8, and 10. Any subset of that set. I can also be the empty set. And here's another subset. Could be 5. From earlier chapters, from the first chapter, we saw that the number of subsets is going to be 2 to the power 10 in this case, 2 to the number of elements in the set. So you can see here that there is a lot of subsets that we can form here. Now, these subsets I, they're used in the theorem to indicate which of the original sets we're going to pick to form the union. For example, for this subset here, we pick set 1, set 2, and set 4, and we make the union. So whatever that union is, we're going to use that in the theorem. For example, here we're going to pick the union S2, 5, S8, and S10. We form the union. The empty set, this indicates that there's no subset that you're going to pick, so it's empty. This is saying that we're going to pick set S5, whatever that is. It's only one set. So these are the unions that correspond to the subset I. Now the theorem is saying that we form the union and we count the number of elements in each union. So we count the number of elements here, and then we check, is the number of elements here greater than or equal to 3? If so, then it's okay. Then we check the other unions and see if the number of elements it contains at least as many elements that the set I does. So this union here, for example, I don't know what it is, but whatever it is, it needs to have at least 4 elements because the corresponding set I has 4 elements. This union here has no elements, so 0 elements, so is this one. And this one, whatever number of elements this set contains, then it needs to have at least 1 element. So Hall's theorem is saying that if all of those are okay, if each union contains as many elements as the set I does, for all these subsets, for all the 2 to the power 10 of subsets, then the Hall's theorem is saying that the original sequence of sets does have an SDR. Let's take a look at this example. Here we have a sequence of sets, only 3, S1, S2, and S3. That means the set I in the theorem will be a subset of the numbers 1 through 1, 2, and 3. So there are a total of 8 subsets. Right? It's 2 to the third power. And here we list all the subsets. So the empty set is there. Sets with one element are there. And then the entire set itself. Now let's form the unions, the corresponding unions. Here, the empty set, that means the union is also empty. Here it's saying that we're going to pick set 1. There's set 1. Here we're going to pick set 2. There's set 2, set 3. Here we're going to pick sets 1 and 2, and you make the union of those two. That's A, B, C, and E. Make the union of sets 1 and 3. Make the union of sets 2 and 3. A, B, and E. And finally, sets 1, 2, and 3. Make the union of all of them. Now look at each union and see how many elements do we have in each union. Here we have 3 elements. That's greater than 1 element. That's good. 2 elements greater than 1 element. 2 elements here and 1 element here. Good. 4 elements, 2 elements. So they're all okay. 4 elements, 2 elements, 3 elements, 2 elements. So this means that there is no violation of the hypothesis of the Hall's theorem. So there is a system of distinct representatives. Okay, so that's what Hall's theorem is saying. So let's go back here. Notice that whenever I is a subset of that set of numbers, so we pick any subset, and each one of them needs to have at least as many elements as the set I does. If that happens, then Hall's theorem guarantees that there is an SDR. You may think that this is pretty tedious because what if we had 10 sets, then we would have 2 to the 10th power subsets here. And we would need to verify each one of them and see if each union has at least as many elements as the set I does. And it turns out that that's exactly what we would need to do. But Hall's theorem is actually used more often in finding out whether there is not an SDR. Because if one of those unions has number of elements that are less than the number of elements in the set I, then the entire hypothesis of Hall's theorem is violated. So there will be no SDR available. So it's only enough one of these to be violated in order for us to conclude that there is no SDR. So that was the key idea in example 6.2. If you see here, look what happens if we take, if we have 4 sets, and here is the set I, the subset of the numbers 1 through 4. If we pick set 1, 3, and 4, we make the union, then we only have 2 elements. So we have 2 elements, but we have 3 elements in the set I. So that violates Hall's theorem, or the hypothesis, right? The hypothesis here, the condition. That means there is no SDR for this example. Now let's go back to our scheduling problem. Here are the 6 courses and the professors, the 7 professors, and we can consider these 6 courses as a sequence of sets, set 1 through 6. And the solution of the original problem is to find an SDR. If there is an SDR, then that will be the solution. Now, if we pick sets 1, 3, 4, and 6, and we make the union, we're going to see only 3 professors. And that violates the hypothesis of Hall's theorem, and therefore there is no system of distinct representatives. Right, so here's the union, 3 elements, and look at the subset I that has 4 elements. So we have 3 elements that are less, 3 is less than 4, so it violates the hypothesis. And you can actually see why there's not an SDR, where there is a problem here. Only 3 professors available to teach 4 of those courses, so not enough professors for those 4 courses. Instead of checking all 288 possible 6 tuples for this problem, the 288 total is obtained by multiplying 3 times 4 times 2 times 2 times 3 times 2, and then forming those 6 tuples and checking each one and see if there is any SDR. Or another way we could do is to use Hall's theorem by examining all the subsets of the set 1 through 6 and computing the corresponding unions. Now, the number of subsets would be 2 to the 6th power, so that's 64. So we would be checking 64 subsets and see if any of those violate, the hypothesis of Hall's theorem. If not, then there is an SDR. If one of them fails, then we can conclude that there is no SDR. Now, for a larger problem, then the number of subsets may be much lower than the number of possible tuples. So that's another way we can find out whether there is an SDR in a problem. It's worth noting here that Hall's theorem doesn't give us the SDR. It doesn't tell us how to find the SDR. It simply says that there is or there is not by checking, all the subsets.